All right, welcome back, everybody. So this lecture today is going to be on multicollinearity. It's actually going to be a very long lecture. We're going to break it up into 3 parts. Um, but yeah, let's just get started. I don't want to give any spoilers. Um, References if you need it. Again, this is going to be a bit meaty, so take in the references if you need them. Okay, so let's start with the least squares estimator. Okay, so we've solved for the least squares estimator. Again, this is in matrix notation, where x is our design matrix, y is a vector of the y observations. And I said way back in the beginning, just believe me here, that this x transpose x is invertible. And I said we'll get to it later. And now is that later. So we're going to talk about invertibility of x transpose x in this lecture. This is related to, but not the complete picture of multicollinearity. Yeah, so we're going to talk about what makes x transpose x invertible. We have also mentioned that in general, so this was some time ago, but we talked about the ideas that in terms of choosing predictors for a model, that if two predictors are very, very highly correlated, i.e., they give me basically the same information. This is bad from the perspective of building a linear model because we're giving redundant information to two different predictors. And in particular, it is bad because it makes the variance of our least squares estimator large. So this is something we'll talk about in more detail in this lecture. But basically what happens is that correlated predictors makes the variance of the least squares estimator large. And again, this is a matrix. So when I say that it's large, I'm referring to its elements, in particular the diagonal terms. These diagonal terms are larger. They refer to the variances. The off diagonals refer to the covariances. We didn't. So this is true. We will talk about this in more detail in this lecture. So it turns out that this high variance is actually fundamentally related to x transpose x being invertible. Yeah. These topics are both related to this certain fact called this certain notion of collinearity. So collinearity is when a linear combination of predictors, so there exists a linear combination of predictors which is equal to or close to 0. So being equal to 0, as it turns out, will give us that x transpose x is not invertible. Being close to 0 will turn out that this variance is very high. Okay, so that's where we're going. So recalling some facts from linear algebra. So recall that a square matrix A is invertible if and only if, here this should be an I here, if and only if any of the following conditions, I guess I have it written correctly, I just read it wrong. So a matrix A is invertible if any of the following equivalent conditions hold. That is, the matrix has non-zero determinant, the matrix has full column rank, or the matrix has full row rank. Okay, full column rank and full row rank means that we cannot come up with a linear combination of columns which is equal to 0 besides the one where all the coefficients are equal to 0, and the same for rows. It has full row rank if we cannot come up with a non-zero linear combination of columns such that that linear combination of columns is equal to 0. Okay. Yeah, the rank in general is the span of the rank of a set of vectors is its span, so the dimension of the space generated by all linear combination of its vectors. And for us, we care about the invertibility of this matrix x transpose x, right? For a special case where A is B transpose B for some matrix B, we care about x transpose x for our design matrix X. This matrix is invertible if and only if the matrix has full column rank. So for us, this condition of invertibility is going to be reduced to the design matrix X has full column rank, that is the dimension of the space spanned by the column vectors is equal to the number of column vectors, i.e. We cannot come up with a linear combination of columns which is equal to 0, except for the ones where all the coefficients are 0. So what all these facts tell us is that X transpose X inverse exists when the design matrix X has full column rank. So this is a certain sort of lack of degeneracy in the columns. Okay, when I say degeneracy, I'm referring to this idea that we can come up with this linear combination of columns which is equal to 0. Okay, so this is some talk about the column space. We're talking about the columns of the design matrix X. We can think about columns more in terms of the hat matrix. Okay, so the hat matrix, which is, remember, the hat matrix puts the hat on Y. One of my favorite names of all statistical concepts. Hat matrix is defined as follows. We've seen it before. We've seen or shown that it's an orthogonal projection matrix, i.e. it's symmetric, right? That means that H transpose equals H, and also it's idempotent, H squares equals H. And so the question here is, it's an orthogonal projection matrix, right? So when you think about something being a projection, sort of, you think about sort of, I don't know, taking a picture sort of as projecting some three-dimensional space onto some two-dimensional space. But the question here is, what space, actually, if it's a projection, what space does it project onto? Okay? So recall that we've shown that H is n by n, where n is the number of observations. I'm going to denote by col of X, the column space of X, the span of its columns. And I'm going to, so here are some linear algebra facts coming at us, okay? So a vector in the column space, the span of the columns, can be written as xw for some vector w. So that is, if a vector is in the column space, it can be written as a linear combination of the columns. Okay, so that is this. Okay, that is column space, linear combination of columns. And another linear algebra fact, you may or may not have seen this one before, but a vector space, okay, so as a space of vectors, can be written as a direct sum of a subspace V and its orthogonal complement. Okay, so that is so in particular we have Rn, so this is the n-dimensional n-dimensional Euclidean space, i.e. n real numbers, can be written as a direct sum of a subspace and its orthogonal complement. So what this is sort of what this is saying. Let me just draw out a quick little picture in case these linear algebra facts are coming at you hard and fast. What this is saying is that this is something pretty intuitive. But it sort of has a lot of math notation. So let's think about the plane, right? R2, n is 2. Okay. So what this is saying is that a vector space can be written as a direct sum of a subspace V and its orthogonal complement. So let's say I give you an orthogonal a subspace V. Okay. So here's a subspace. V goes through the origin. It's all multiples of this vector, which is 1, 1. Okay. And then what this says is that the R2 can be written as we can decompose R2 into 1, 1, and it's the space that's orthogonal to it. Okay, so in this case, this is 1, negative 1, the span of this vector. Okay, so basically what it's saying is that we can basically decompose a vector space, a space of vectors, into a subspace and all the things that are orthogonal to it. And then we can write every point here as how much do I need, how much coefficient do I have in one subspace plus how much coefficient do I have in its orthogonal subspace. Okay, so but here I'm just writing, instead of having these two different lines, we have sort of planes where we think about V and V perp, the orthogonal space, but this is just all the vectors that are orthogonal to V. But what this is saying is we can decompose Euclidean space, the space of n real numbers into a subspace and its orthogonal space. Okay, and as the picture suggests, it's kind of intuitive, right? You sort of break it down into how much you'll have in V, how much you'll have in V perp. Okay, it is a linear algebra fact that the space that's orthogonal, so that is all if you take the column space of X, right, everything that's orthogonal to that, okay, that is equal to the null space of X transpose. Okay, this holds for any matrix, not just the design matrix, but we're just going to use it here in the context of the design matrix. So we have a couple of facts building up. So we say we can write the column space as a certain way. We can decompose a space into a linear subspace and its orthogonal complement, and then we have that the orthogonal complement of the column space is equal to the null space of X transpose. Okay, so we have a couple pieces moving around together. Let's go ahead and apply them. So we're going to use all these facts from the previous slide to show what the hat matrix actually projects on, right? So if you assume so let's just go back to this assumption that the inverse of X transpose X actually exists. Okay, so I have any matrix or any vector Y in Rn. So this is a vector of my observations of the Y variable. I'm going to apply the hat matrix to Y. Okay, and remember that any vector in Rn by this Rn can be decomposed into V plus V perp. It can be written as a sum of an orthogonal space and its orthogonal space, right? So what I'm writing this vector Y as is how much of it is in the column space, that's V, and then how much of it is in the orthogonal complement, that's U. But we know that the orthogonal complement from this last fact here, so orthogonal complement is actually equal to the null of X transpose, right? So what I'm doing here is I'm saying, okay, let's do HY, but I can write Y as the part that's in the column space and the part that's in the null space of X transpose. And remember, I should say this in case it's been a little bit since you've taken a linear algebra class, but the null space of a matrix is the null space of a matrix A is all the vectors that get mapped to 0 by A. So the null space of X transpose is all the vectors that get sent to 0 by X transpose. Okay, that's why the word null space is appropriate. Okay, so we have Y can be written as some part of it's in the column space of X plus some part that gets sent to 0 by X transpose. Okay. V, because V is in the column space of X, by this fact here, we can write any V in the column space of X as XW for some vector W, right? So I'm going to take V, I'm going to rewrite it as XW, okay? So again, this is just for an arbitrary Y. I can say, well, arbitrary Y can be split into these two pieces. The column space can be written as XW for my design matrix X and some vector W, okay? Expanding out the definition of H, so this is just what the definition of H is, okay? And then I'm go ahead and expand. So I'm going to distribute this X transpose X inverse X transpose to both of these terms, okay? But remember, U is in the null of X transpose. So what that means is that when I apply X transpose to U, I get 0, just by its definition of being in the null of X transpose. So when I distribute this piece to U, I get 0, okay? This piece, well, I have an X transpose X inverse and an X transpose X, so these cancel, and I'm left with XW. So I get XW, okay? And XW, remember, XW is equal to V. So what just happened here? Okay, we just did a big derivation, but what we showed is that well, Y can be decomposed into the part that's in the column of X, the column space of X, and the part that's in the null space of X transpose. And when we apply H annihilates that U component, and we're left with the part that's in the column space of X. Okay, so when we apply the hat matrix, we only keep the part of Y that's in the column space of X, right? And so in the context of, for example, this picture here, what's happening is we're decomposing into two different spaces. We have a column space of X, null space of X transpose, and we're just keeping the part that's in the column space of X, okay? And so what's happening is we are projecting Y onto the column space of X. We are throwing away the orthogonal piece and projecting onto the column space of X, okay? So this is the space that H projects onto. So yeah, hope that wasn't keeping you up at night. We've talked about this idea of orthogonal projection. I suspect it wasn't for most of you, but we have answered the question by just breaking this down and using a little bit of linear algebra facts. Here's a cleaner picture than me sketching, and what it shows is that we're taking this space Rn, we're decomposing it into the column space of X and what's orthogonal to it, the null of X transpose, and then H is a projection. We're basically taking an arbitrary point Y. If you apply H to it, you are left with just the piece that's in the column space of X, and you annihilate the part that's in the null space of X transpose. Okay. Okay, so great. So yeah, we project onto the column space of X. Let's sort of combine this into a couple of facts. So we know that X transpose X, as we discussed a couple of slides ago, it's not invertible when X does not have full column rank. This is rewritten in the linear combination form, so it's not invertible when we can find a non-trivial linear combinations of the columns, okay? And by what I mean by non-trivial here is that these AIs cannot all be equal to 0, such that when you sum up the columns, you get the 0 vector, okay? So because of this, the least squares estimator only exists when X has full column rank. That's because we cannot define this X transpose X inverse X transpose Y unless we can take this inverse. So the least squares estimator only exists when X has full column rank. The design matrix, that is, has full column rank. But when there is a linear combination, so if we have a linear combination which is close to 0 but not equal to 0, so let's say we can get sort of very close to 0 with this linear combination. We're near 0 but not equal to 0. X transpose X inverse, but X transpose X inverse exists, but it begins to blow up, okay? So similar to the fact that, you know, if you have something like, this is what I've written here at the bottom, but if you have something like 1 over X, right, for a scalar X, right, as you take, this is equal to X inverse, right, as you take X for a scalar, as you take X towards 0, X inverse, 1 over X, blows up, right, gets very large. Similarly, when you're trying to invert X transpose X, but your linear combinations, but there's a linear combination of columns which goes very close to 0, similarly, the inverse begins to blow up, okay? Its values get very large, okay? And so a special case of this, so in particular, so when does this happen? We have these linear combinations which are very close to 0. Special case of this is when two predictors are very strongly positive or very strongly negatively correlated. So when they're correlated very strongly, what this means is that, so for example, you have x1 is, I don't know, is approximately negative 1.4 x2. I'm just picking some numbers up. If this is approximately true, right, then they're going to be very strongly negatively correlated. You have this linear combination. When you subtract over, you have a combination which is x1 plus 1.4 x2, which is approximately equal to 0, and you have this blowing up of the inverse. Okay, so this is going back and connecting to this idea that two predictors which are very highly correlated are not useful in a model, and in particular they can hurt us because this X transpose X inverse begins to blow up. Okay. So linear combinations of predictors which are exactly or approximately degenerate, and by degenerate I mean equal to 0, This is the problem of collinearity. Okay, so multicollinearity refers to the fact when we have multiple vectors in this linear combination, which can be which produce a degenerate linear combination. Okay, so we're going to talk about how to detect collinearity, okay, using what's called the variance inflation factor. So the variance inflation factor is going to measure how much does the variance of beta hat, the least squares estimator, increase when using all of the predictors instead of a single predictor. And we'll show why this is related to this x transpose x inverse being very large. So we're going to introduce the variance inflation factor. We're going to introduce the eigen decomposition. This is going to come in the part 2 of this lecture. But we're going to have the eigen decomposition and the variance inflation factor for detecting collinearity. Okay, and then we're going to talk about how to fix collinearity in the third part of this lecture, where we're going to introduce throwing out predictors which are causing degeneracy. We're going to be able to use this eigen decomposition of the variance covariance matrix of the vector of predictors x. We can throw out predictors which cause degeneracy. We can use a certain regression technique called ridge regression. Again, this is all coming, but this is a summary. And lastly, we're going to do 3 techniques for fixing collinearity: ridge regression, principal component regression, and 2 to detect. Okay, so this is going to be today, and then in the next lecture we're going to do eigen decomposition, and then in the third lecture we're going to do fixing collinearity. So you might feel at the end of this lecture, oh, I only know how to detect a problem, I don't know how to fix it. It's coming. Okay, so let's talk about the variance inflation factor. So the variance inflation factor, we will start with simple linear regression in matrix format. So when we have a single predictor, xi, we can build a design matrix. And I want to know the variance of the least squares estimator. Okay. We've actually seen the covariance matrix. So the covariance matrix, this is under the second assumption. So remember, the second assumption on epsilon was that the epsilons have constant variance and are uncorrelated across observations. So we've seen this previously in the multiple linear regression lecture, that when we have this second assumption, we can find the covariance matrix of the least squares estimator, and it is this, where sigma squared is the variance of epsilon. Okay. If you use some algebra and you take the matrix inverse of a 2 by 2 matrix, you can show that the variance of the ith term of the least squares estimator is equal to the following, right? So what I'm doing is basically just saying you can break out this matrix. You can take the diagonal terms, which give you the variance, as opposed to the covariance on the off-diagonal terms, and you get this expression. Sigma squared hangs along, and the diagonal term of this matrix is equal to this piece here. Okay. In multiple linear regression, okay, so this was as opposed to simple linear regression. So if we're in multiple linear regression, the variance of the ith term, okay, is equal to, well, it's the I plus 1th term in the diagonal of the variance covariance matrix. Okay, so here I'm being just a tiny bit sloppy, but I hope it's clear that this design matrix in multiple linear regression have multiple columns. In simple linear regression, we just have 2 columns, but the form is the same. The I plus 1th term is because beta 0, we've seen this before, but beta 0 corresponds to the first term along the diagonal, beta 1 to the second, and so on and so forth. So the I plus 1 term is because we count the betas according to 0 first, but the index along the diagonal with 1 first. It turns out that the best case of for the variance of beta hat, i.e. we want the lowest possible variance, low variance is good in an estimator, is simple linear regression. Okay, so simple linear regression gives us the lowest variance possible in beta hat, and so what VIFS, the variance inflation factor, tries to answer is how much does the variance of one of the coefficients of our least squares estimator, increase for multiple linear regression. Okay. So the variance inflation factor is defined as the ratio between the multiple linear regression variance and the simple linear regression variance. Okay. So what happens here is we're looking at the variance inflation factor and we're saying, okay, let's say we've added some predictors to our multiple linear regression model, which are nearly degenerate, right? So we have this near degeneracy of the columns. We have a linear combination of columns, which is near zero. X transpose X inverse it exists, X transpose X inverse, but it gets very large because of this near degeneracy. Then what's going to happen is that the variance inflation factor is going to say, okay, well, in the multiple linear regression model, you have very high covariance, or very high variance of the ith term because X transpose X inverse is getting very large relative to the simple linear regression variance. Okay, so this is the definition of the variance inflation factor. When you take the ratio like this, the sigma squareds cancel, which is good because in practice we don't usually know sigma squared, so we can actually compute the variance inflation factor with this expression. Okay, keeping in mind that this is the design matrix for the multiple linear regression model, and this is the variance for a this is 1 over the variance of a this comes from a simple linear regression model with the ith predictor only. Okay, so the variance inflation factor is again what it's computing is how many times larger is the multiple linear regression variance compared to the simple linear regression variance for that predictor. Okay, this is important because this is related to the fact that X transpose X inverse begins to explode as we have near degeneracy in our design matrix. So a fact is that the VIF is always greater than or equal to 1. So the variance inflation factor is always greater than or equal to 1. The reason for this is that the simple linear regression variance, as I discussed, is the best case of the variance. Okay, so this is the smallest variance we can have is using a simple linear regression model with a single predictor. And so the smallest that this can be is, well, this denominator, so the smallest that this variance inflation factor can be is 1. Okay, so it's a fact, variance inflation factor is always greater than or equal to 1. Some folklore here is that if the VIF of one of your coefficients is greater than or equal to 10, okay, so as any of your predictors, your VIF is greater than 10, then collinearity is a cause for concern. Okay, I call this folklore not because I intend to actively undermine it, but I kind of do. This is tradition. Okay, is it true that VIFs, at 10 are bad, at VIFs at 9.9 are not bad? No. This is sort of just an arbitrary cutoff rule which people use to sort of you should dig into your multicollinearity issues a little more if your VIFs are greater than 10. But it's like any rule of thumb, it's a heuristic, right? So it's ballpark, and it's been passed down to us by people who have come before us. We don't have any strong reasons to change it, but it's a folklore result similar to the central limit of the theorem applies for sample size greater than or equal to 30, right? Just it's this hard line that we draw in the sand. It's handed to us from statisticians who have come before. Not exactly true, but a good heuristic that we can use in practice. So to calculate VIFs in R, you can do a couple of things. You can calculate it by hand. By hand here, I mean actually do this computation in R, compute these inverses and things like this. We're only going to do this a few times to make sure that R's computing VIFs under the hood as it's supposed to. You can use the CAR package. CAR stands for Companion to Applied Regression. It's a textbook written by the author, whose last name is Fox, and I forget his first name. Anyways, in this CAR package, there's a function called VIF. It will compute the VIF of a linear model. You feed it in a linear model as an argument. It'll output the variance inflation factors. I will make a small note here, okay, but please pay attention to this note. Variances are only defined for numeric variables. Okay, so note this, right? If I have this variance inflation factor, I'm taking the variance inflation factor and these x's when they're categorical. So when I have binary predictors, as we've discussed in the 2 lectures ago, right? We talked about binary predictors where we're coding our categories here. The VIF loses its invalid interpretation as this is what's happened to each of the predictors, and the reason is that we code one categorical predictors across multiple columns of the design matrix, right? You sort of take a category, you take a predictor which is categorical, which has 4 categories: category 1, category 2, category 3, and category 4, and you break it up into a reference category and 3 binary predictors, right? And so when you do that, you cannot interpret the variance inflation factor as saying something about all these categories at once. Okay, so the variance inflation factor loses much of its charm. There is a thing called a generalized variance inflation factor. It's a generalized VIF, and the CAR package will use it for categorical predictors. So the CAR package will basically use some other technique, which we're not going to discuss, but I just want you to know that it exists. And what it will do is it will take all these binary predictors and combine and compute a generalized variance inflation factor to tell you the variance inflation factor of using this predictor with all of these categories at once. Okay. So the moral of the story with the generalized VIF is that you can interpret it just as you would the usual VIF. So in that sense, if the generalized VIF is greater than or equal to 10, collinearity is a cause for concern, so on and so forth. But VIFs, there's a problem when you use categorical predictors. There's an extension called the GVIF, the generalized VIF, which you can interpret exactly as you would the VIF. So when you see it using the CAR package, don't be alarmed. But we're not going to discuss the generalized VIF in detail because we're just going to introduce other methods instead. So please remember this. You will see this if you try and compute VIFs using categorical predictors. Okay, so let's look at a quick example. So I have 3 different models that I'm going to consider. So this is going to be a simulation I'm going to do. I have a low noise model. Okay, so I have a low noise model where y depends linearly on 2 predictors, x1 and x2, and I have some noise epsilon. The noise epsilon is normal, mean 0, variance 1. I have a high noise model where x and y are related exactly as before. Okay, and my epsilon has high noise, variance 100. And then I'm going to have a correlated predictor model. Okay, so in these first 2 models, what I'm going to do is I'm going to generate a sample of x1 and x2, which are independent. Okay, they're independent and normally distributed. For my correlated predictor model, what I'm going to do is I'm going to take y related to x in the same way. Okay, I'm going to take the small noise version, that is epsilon is just equal to, or the variance of epsilon is just equal to 1. But then instead of generating x and y independently, I'm going to generate x as I did before, x1 as I did before, and I'm going to generate x2 by adding just a little bit of noise to x1, this delta term. So what I'm doing with this last model is I'm constructing predictors which are going to be highly correlated, right? They're going to say almost the same thing, but there's going to be some slight noise between them. Okay? So I'm going to compute the variance inflation factors for these 3 models and compare them. We have a high noise model, a low noise model, and a correlated predictor model. So this is the one which was going to get at this idea of multicollinearity. We have some collinear predictors. x1 and x2 are not perfectly degenerate, right? Because if I subtracted x2 from x1, have something which is near 0, this delta term, but not 0. So yeah, let's see what happens here. So this is a plot of the least squares estimator for 100 samples of each model. Okay, so this takes just a little bit to explain, but what happens is I generate x1, x2, epsilon, and y for 100 times for each model. Okay, I'm going to solve the least squares estimation problem given all those points, right? Just my x and y points. I'm obviously not going to use my epsilon to do the least squares estimator. I'm going to do the least squares estimator like I know how to do. come up with beta 1 and beta 2, the estimates of this 4 and 8 term. Okay, and that's what I'm plotting here, is the plots of the least squares estimator, the 4 and the 8 term, that my estimates of the 4 and the 8 terms for the three different models. So I have the truth, 4, 8. The green noise gives the 100 estimates for the low noise model. The red points give the 100 estimates for the high noise model. And then the blue points give me the 100 estimates for the correlated model, where x1 and x2 are related. So this is kind of strange, right? So we see that the error sort of looks approximately, there's this little circle that we can draw for the green model. For the red model, the circle gets larger. But for the correlated model, the error, being, if I overestimate beta 1, then I underestimate beta 2, right? So here we have correlated errors, right? So what's happening is that the variance of beta hat, right? This is as here I've just written it for beta 1 and beta 2. I'm omitting beta 0 just for the sake of this plot. But the covariance matrix between beta 1 and beta 2 is going to have some high values on the off-diagonal terms, right? I guess these are large and negative, right? Because this beta 1 hat and beta 2 hat, they're negatively correlated, right? Strongly so. This is I want to say high value. I guess it's negative high in absolute value, but I hope you know what I mean. Because what's happened, you see that the spread of these points, even though the epsilon added to this model has variance 1, the correlation is making it so that the variance is blowing up, right? And so you can imagine if you wanted to make an estimate, let's say you wanted to estimate these betas, and you had correlated predictors, it's quite hard to do it when they're correlated, even if you have low noise, because you end up with errors that look like this, sort of systemic errors where beta 1 and beta 2 are negatively correlated. And also these blue points are just way more spread out than these red points are in general. So this demonstrates some of the problems that will happen with correlated predictors. For those three models, I can compute the VIFs. So if I compute the VIFs of the low noise model and the high noise model, I see that the VIFs are small. Okay, so what's happening is adding the second, so this is when I go from a single predictor model with x1 to a multiple linear regression model with x1 and x2, the variance of the beta 1 hat term doesn't increase very much. Okay, same for beta 2. But when I look at the correlated predictor model, what happens is the variance of beta 1 hat in the simple linear regression is much smaller than the variance of beta 1 hat in the multiple linear regression model where I've included both predictors. Okay, so the variance inflation factor here is picking up on these systemic errors, the fact that our predictors are very highly correlated. It shows up in that x transpose x inverse, which shows up in that ratio of variances we were talking about earlier, and our variance inflation factor is very large, much larger than that folklore rule of thumb that we use to distinguish between if the VIFs are cause for concern, much larger than that 10 value. Okay, so next we're going to demonstrate how to replicate this example, how to do the simulations. We'll do that quickly, and we'll spend more time on calculating VIFs in R. So let's jump over to R here. So here I will construct three models, the three models that I talked about, low variance, high variance, and low variance with correlated predictors. I'm going to compute the VIFs by hand and with the CAR package, this companion to applied regression. When I set my seed here, I believe I mentioned this before, but when I set my seed here, what this does is that when I run this example again, I'll get the same randomness generated. So this is random. This is reproducible randomness in the sense that the random numbers that are generated will be the same if I set the seed. So generating x. So this what I do here is I'm generating x's from the first model and the first variable here. This is how my naming convention goes. The first x in the first model's first x, the first model's second x, and then generating the epsilon according to the rules as the expression that I had on the slides. So this is variance 1, and then I generate y according to that relationship, where beta 1, the true beta 1 and the true beta 2 are 4 and 8 respectively. The design matrix. So I can either use model.matrix. So model.matrix is a helper function that will generate a design matrix for me. Alternatively, I can do it as we've done before, where I combine the ones column, the first predictor and the second predictor. So this is my design matrix. And then what I'm going to do to compute the VIF is I'm going to compute X transpose X inverse. Okay. And let me just pull this back up to reference it. I'm computing this thing. So I'm going to compute X transpose X inverse, get the I plus 1 terms along the diagonal, multiply it by this expression here, which is for the ith predictor, I'm going to take, basically, this looks like something like a sample variance, except for I haven't divided by the n minus 1 out front. So this is the sample mean of the ith column, and I'm taking the squared difference between all of the observations from that predictor and the sample mean. Okay, so this is the X transpose X inverse term. The simple linear regression part of the VIF is what I'm going to do is I'm going to apply to this design matrix. So this is just a way to do the sum of X minus its mean squared. I'm going to apply it to all the columns of the design matrix simultaneously. So this gives me that that sum of the predictor minus the sum of the squared difference of the predictor values minus its sample mean for each of the observations. And then to find the actual VIFs, I take the product of those two, as we saw in this expression. So I'm taking the product of the diagonal bit and the simple linear regression bit. Okay. And so there are my VIFs. So these are my VIFs calculated by hand. By hand, I mean calculated in R, manually using the diagonal of the X transpose X inverse matrix and this simple linear regression bit. Loading up the CAR package, I can compute the VIF of that linear model directly. So much easier to use the CAR package, and I encourage you to. I may ask you to compute it to compute the VIFs by hand once or twice, just to make sure you can actually do it and you're comfortable with that linear algebra procedure in R. But in practice, use the VIF package. We see that it's actually doing exactly what we did under the hood. The only thing is that we did a variance inflation factor for the intercept term, which actually isn't necessary. For the second model, things worked exactly the same. I'm not going to spend that much time on it. The only thing I'm going to highlight is that we use a variance of 100 here instead of a variance of 1 in our epsilon term. I'm going to compute my VIFs exactly the same. I see my VIFs match exactly what the CAR package and the VIF function from the CAR package outputs for me. Okay. Lastly, for the correlated predictor model, I'm going to generate some x's. Here, again, I'm generating x2 as x1 plus some delta term, which is small. Okay, so it has low noise, so x2 is very similar to x1. My noise term, again, this is a low noise version, so even though it's low noise, like the pictures, like the green points in the plot in the slides, it ends up being very spread out because of the correlated predictors. My relationship between x and y, my design matrix, the multiple linear regression part of the VIF, the simple linear regression part of the VIFs, taking their product. Here's my VIFs. You can see that my VIFs, again, are very, very large, much larger than that 10 rule of thumb that we talked about before. And again, the CAR package matches exactly what we have. So we confirmed that the CAR package actually does what we expect it would do, and we've confirmed it by these three examples. The plots here that I have below, if you're looking through this code, the plots will just produce the plots that I have on the slides here, where I have these, where are we here? Where I have these pictures. So if you want to follow along, I will post that code. But otherwise, that's all I have to say about VIFs, and we will pick up later talking about the eigendecomposition of the covariance matrix, which will be a lot of fun. So, yeah, see everybody next time.